Part 2 of my online lectures on risk. Let's get started. So as we remember from the first video, fitness is a nonlinear function of returns or effort or whatever it is we want to call it. We indicated that the outcome of our decisions as x, and we called fitness f of x. Okay, and we have a function. F of x is increasing in x, but it shows diminishing marginal returns to x. So it has a positive first derivative and a negative second derivative. Okay, and what we're going to do is we're going to label a couple points on the x-axis here. Actually, why don't we co-opt this and call it xh, xl, and then the mean of those two is x bar. Okay, and I'm also going to draw a dotted line here. Hopefully I'll get it right. When in doubt, extend the curve a little bit. That's a chord that connects the values of f of x according to f of x of L and f of x sub h. Okay, so let's draw a line from x bar up, because we're just assuming that there's a coin flip, 50-50 chance you get either xh or x sub L. The mean return, right, the mean fitness of this lottery is going to be given by the x bar, the fitness of x bar, right? Well, let's think about two things here. We're going to draw this line all the way up here. In fact, right, the expected value, the fitness of the expected value is there. The expected value of fitness, because this point is the average of this and this, right? So this is the fitness of the expected value of x, and this is the expected value of fitness. Those are very different, aren't they? And that shouldn't be surprising, because in the last video, we showed, using the simple Taylor series expansion of a fitness function and then taking expectations of it, that variability is going to reduce fitness from what you'd expect from the function of mean fitness, right? So this should be expected. Okay, but what I want to do is help develop our intuition a little bit about what this gamble looks like and why this shape might look like this. Why this big difference between the fitness of the expected outcome and expected fitness. So let's think about what this gamble looks like. If we're here, we're at the fitness of the mean, and we take a gamble that has a 50-50 chance of going up or down by a unit, going up to x sub h or going down to x sub L. Draw this, that's how much we'd go up. And that's how much we'd go down. You see that there's an asymmetry there, and that asymmetry arises, not surprisingly, from the shape of the fitness function. We refer to this decrease here as the downside risk of the gamble. We refer to this increase as the upside risk. Remember that risk isn't necessarily negative, right? It just means variable. It turns out to have lots of negative implications for fitness and that sort of thing, but getting more than the expected value is just as much risk as getting less than the expected value. Okay, so the curvature of f of x creates a substantial asymmetry between the downside and the upside risk. And what we say of someone who has a preference function that looks like this, whether or not it's in their head or whether or not it plays out as a function of population dynamics and fitness differentials, we say that this person is risk averse. This is the definition of risk aversion in the economic sense. It arises from the curvature of a fitness function. Okay, so we've seen that variance is generally bad for mean fitness, right? Because that second term in our expansion is negative, and so variance is going to drag down the mean fitness from the fitness of the mean outcome. And we've seen that this leads to risk aversion. What we're going to look at now is a situation that we call the risk premium. So if you're a risk-averse decision maker, you should be willing to pay for certainty. And how much should you pay for certainty? You know, you pay a little bit of a premium and you get a certain outcome. What's the value that you should be willing to pay? This is like insurance, right? You pay a premium for your car insurance or your life insurance or your home insurance, and you receive a payout if you have a catastrophic outcome, and it mitigates the risk. It manages the risk of a catastrophic outcome by paying a little bit of a premium. Okay, so let's draw our curve again. Dotted line, chord that connects them, and we have x bar here, xh, xl. Okay, draw from the x bar up to the point on this chord, which is the mean fitness, right? This is again, and up here somewhere is the fitness of the mean return. Okay. Now note that this point doesn't actually touch the fitness curve. Okay, and so we can actually take this back horizontally to the fitness curve, and all of these values have the same fitness, right? That's the point of it being horizontal on this fitness function. Now we'll change the color of the pen. This value of x here is what's called the certainty equivalent. Okay, that's the value that you should be, that's the certain value that you should be willing to trade for the gamble. Okay, and the difference between your certainty equivalent and, oops, didn't mean that, and your mean your mean outcome, we call that pi, and that is called the certainty premium. Pi is the certainty premium. It's the difference between these 2 points here, and it's the amount that you'd be willing to pay, given a gamble, to get a certain outcome, x sub c, which is the certainty equivalent of the gamble that you're playing. We will talk about a little bit more about the curvature of our fitness curve and how that interacts with variance, and how we can use that to estimate what the magnitude of the certainty premium is going to be for a given fitness function. But we'll save that for the next video.